In section 6.6, we're going to be looking at some proportionality theorems in triangles. And the first one is, well, it's called triangle proportionality theorem. It deals with if you have a line parallel to a side of a triangle intersecting the other two sides, then it divides those sides proportionally. You notice in this case, a line parallel to one side of a triangle. This is this line, TU, parallel to a side of the triangle, QS. You notice they're parallel by marks. If it intersects the other two sides, it divides it proportionally. Okay, a line parallel to one side divides these two sides basically into proportional segments or proportional parts. So I want to fill in the if-then statement below here. After if, it was basically if we have a line parallel to one side of a triangle. So I have this line TU in the triangle. It's parallel to this side QS. And maybe I shouldn't really have the lines here, it's more of a segment. But if you have one line in a triangle parallel to a side, then it intersects these two sides proportionally. So I'm looking at the parts of these sides. So I'm looking at QT, like that portion of that side, compared to the other portion of that side, TR. So this part, QT to TR, and that would be the same ratio as SU to UR. It splits that side exactly the same way. Okay? And that's not the only way to write that. So you notice I wrote from this top side and I did this short part to the longer part to the vertex. And then on the bottom side I did the short part, longer part to the vertex. You could also look at it this way and say I'm going to compare the short part up top, QT, compared to the short part here, SU, or the portions between the parallel lines. And then I started up here, so then I can do TR compared to UR and look at the two portions of those segments that go from the parallel line to the vertex. So I guess two ways to write this, but you notice it's the same exact way. QT and UR are still diagonal. All I did was flip TR and SU where they were in the diagonals. But since we solve a proportion by cross multiplying, as long as things are in the same diagonal, it's still the same proportion. And then we actually have the converse of that triangle proportionality theorem. Remember, the converse flips the if and then. So if you have a line in a triangle and it divides the two sides proportionally, so we're looking at how these two sides were split by this particular line. If these are proportional, then this line must be parallel to that third side. So it's all about testing whether this line is parallel to that side or not. So if I look at it and I see a proportional situation, then I know that this line would be parallel to that side. Let's check it out. So if I look at 6 compared to, now I can compare it to 8 or I can compare it to 9. Okay, you can do it either way. Maybe I'll go 6 to 9. If that's the same as 8 to 12, notice I went 6 to 9, then I would have to do 8 to 12. And is it? Well, I can check by cross multiplying. 6 times 12 would be 72. 9 times 8 is also 72. So yes. Then I can say that this line and this line are parallel, and I can mark them as such. Okay? So if those were not proportional, I would know this line was not parallel to that third side. So it's all about testing whether that line is proportional to the side if it splits the sides proportionally. So let's do some examples. I'm going to find x. And I can because you notice this line that goes in the triangle is marked parallel to that third side. Therefore, it's cutting these sides proportionally. So I know, maybe I'll compare the tops here from the parallel line to the vertex. So if I compare x to 15, notice I went from left side to right side up on the top. Then I can go from left side to right side on the portions that are on the bottom, so 12 to 20. And I know that that's a true proportion since these lines are parallel. It splits these sides proportionally. I cross multiply here. I get 20x equals 180. Divide by 20. And x equals 9. And that looks correct, right? 9 here to 12, 15 to 20 looks good. So triangle proportionality theorem there. Let's look at another example. A brace is added to a tree house. The brace is this green colored segment. Is it parallel to the floor? So did you do a good job in the construction? Did you make this brace parallel to the floor? So really you're thinking, I need to test whether these sides were split proportionally. Test if the sides were split proportionally or not. If they are, yes, the brace is parallel to the floor. If they're not split proportionally, then your brace is not parallel to the floor, excuse me. So I could compare this side and maybe look at the part on the top to bottom, so 22 compared to 28. And see, is that, so I'm putting a question mark, is that the same as 20 to 24? And remember, you can always reduce these, or you can do the cross products and see if those are the same. 22 times 24 gives me 528. 28 times 20, that gives me 560. So these are not equal. Therefore, the sides are not split proportionally. So is the brace parallel to the floor? No. And that's by converse of triangle proportionality theorem. Because I find that the sides are not split proportionally. Therefore, that side is not parallel, or excuse me, that line through the triangle is not parallel to the third side. Okay, so it was not split proportionally. Again, I could have reduced these and found that the ratios weren't the same. I did the cross products instead, found that those were not equal. Sides are not split proportionally, therefore that side is not parallel to the line that divided it to the brace. Alright, this is the best example and definitely the trickiest example so far. I notice in here I do have a parallel line going through a triangle. It's parallel to that third side. Therefore, I know that these sides are split proportionally, which will help me find x. This is what we've been doing so far today. So if I compare, maybe I'll compare 35 and x. I'm comparing those parts of the segments. I'm on top to bottom, so I can compare these parts of the segments, in this case 49 to 42, top to bottom again. And let's cross multiply to find x. So I get 49x equals 35 times 42 is 1,470. Dividing by 49, is 30. Does that seem like a reasonable number? Yeah, I'd say 30 looks pretty good. Here's where you need to be careful, is in finding y. Because if you think about what y is a part of, y is a part of this huge triangle. And now I'm going back to similar triangles, and I know these triangles are similar, actually by angle. With parallel lines, if you think about it, these two angles here are corresponding angles, right? They make that same shape off of the parallel lines. They're both above the parallel lines and above the transversal. I also know that these angles here are corresponding angles and congruent. Again, corresponding angles. They're that same orientation off of the parallel lines on the transversal. And also, this angle is in both triangles, the small and the large. But you have to be careful here, because y is in the large triangle. And I have to use similar triangles here to set up a proportion. So when I compare y to a corresponding side, well, obviously this side of y would correspond to 28 in the other triangle. The tricky part is what else can I pick with y? Because now if I put something else on top, it better be from the same triangle as y. But y is in the large triangle, so you can't just pick 35. You cannot just pick 49. Y is in this triangle. I need this entire side. Okay, so just be real careful with that. We're doing 35 plus 49 in this case. That entire side length is 84. And 84 would be a length in the same triangle as y, so that can go on top. Now what goes on bottom? Well, since I did y was in the big triangle, 28 was in the smaller triangle. And now I picked 84 because that's in the big triangle. What's in the small triangle that corresponds with 84? Well, it'd be the smaller triangle's portion of this side, which is 49. So being really careful about what we're picking when we set up to find y. Now we can cross multiply, and I get 49y equals 28 times 84, 2,352. Divide that by 49, and it looks like y equals 48. Does that seem like a reasonable answer? Yeah, I'd say 48 sounds good for that length. Okay, so being really careful finding that, because here we're using the similar triangles. We're not using proportionality theorem in finding y. We did to find x because we were splitting sides, but keeping in mind y was in the large triangle. All right, in example 4 here, determine whether line PS is parallel to line QR. PS is this random line going through the triangle. To find out whether it's parallel to QR, we're going to have to see whether this line split these two sides proportionally. Now I want you to do the work on this. I want you to test, are these sides split proportionally by this line segment going through the triangle? And then I want to know, are the triangles similar? So is this smaller triangle similar to the larger one, and why? And if they're similar, I need you to find x. So you're doing all of this for tomorrow. We're going to talk about it in class. This is kind of your homework from the notes. When you look to find x, be careful. X is in this triangle, and it's the bottom side, which would correspond with 84. But 84 is in the large triangle. So just like the last example, be really careful finding that. Looking at triangle proportionality theorem today, and looking at how if a line is parallel to the side of a triangle, it splits those sides proportionally. And I want you to do this example 4 for tomorrow.